So now that we've talked about what reactive programming is, and I've motivated it a bit, talked about the different principles it embodies, talked a little bit about how it maps onto some of the features in reactive programming frameworks like RxJava and Project Reactor, and compared and contrasted with different object-oriented and other ways of doing functional programming, let's now start narrowing our scope into the discussion of the key classes in the Project Reactor API, since that's what we're going to be focusing on. And we're going to focus on monos and fluxes, and then a variant of a flux called a parallel flux, very briefly. Now, your upcoming programming assignments are going to start using these features, and what's interesting about this is you're also going to get a chance to see how monos and fluxes are baked into the features that you get with another variant of Spring called WebFlux. So understanding these reactive types will be very important for the bigger focus of our class, which is on developing scalable microservices. So there are two key classes in the Project Reactor API, and the first one is the mono, and this is a class whose objects will complete successfully or not, and thus may or may not emit a single value. This is very similar to a Java completable future or an async optional if there were such a thing in Java. In fact, you can combine completable futures with optionals to get much the same effect here. And we're going to talk a lot about monos. You actually will use them sparingly. We're going to use fluxes primarily, but monos have their role, and you'll get a chance to see how they work. Monos, and fluxes for that matter, can be documented via marble diagrams. And why do we need these? We need these because it's a little complicated at first to get your head around what the heck is going on with reactive programming. And so we use these to try to visualize the behavior of operators. So there's a timeline here where time flows from left to right. And this little circle here is the optional item that'll be emitted by the mono. And this is the operator that's going to be applied to do something to the mono. You can filter it, you can transform it, and so on. And then there's a name inside the box that says what it does. It's usually a name like flat map or due on success or something like that. And then we get an output that is the result of the transformation. And if things succeed, then we have this little vertical line that says we're done and everything's happy. And if something goes wrong, then we get this little X, which says something went awry, usually having to do with an exception or some other problem you might have had. There's a large number of operators that work on monos, and I won't read them all here right now, but we'll talk about all of these in due course. And these are things that you can do to apply transformations or filtering to monos. More common, especially for our use cases, because we're dealing with groups of things, like groups of movies or groups of quotes or whatnot, is something called a flux. And a flux is a type that can emit an indefinite number of events, meaning 0 to forever, or not, 0 to finite, 0 to infinite. And it may complete successfully, or it may complete with failure, again. You can think of a flux as something like an asynchronous Java stream. In fact, you can use completable futures with a Java stream to do something very similar to what we get with fluxes, although fluxes are a little bit more fulsome, as I mentioned before, because they combine those intentionally, whereas completable futures and streams have to be used together in a little bit more of a shotgun marriage-like approach, although they do work quite nicely. One of the other things that you get with a flux is support for so-called back pressure. And this is important whenever you start dealing with asynchronous communication. Because with asynchronous communication, what happens is it's possible for a fast sender to overrun the processing and storage and memory capabilities of a slower consumer. So a fast publisher can overrun the resources of a slower subscriber. And you'll get a chance to see how that works, and you can control that through something called flow control or rate control to determine how quickly things are sent, or how many things are sent. I'll tell you a funny story. When I was a lowly grad student many, many years ago, I had a PhD advisor who was Japanese and wonderful guy, and he, when I first joined his lab, I would listen to him on the phone, and he would end almost every sentence in Japanese, because he was talking to his colleagues or family or whatever, with "hai." And if you know anything about Japanese, "hai" means, I have received the last buffer of information from you, please continue. It does not mean I'm super friendly. That's what I thought at first. I'm like, this is the friendliest guy on the face of the earth. He says hi after every sentence. It's amazing. And it turned out that it was a flow control mechanism that says, I received it, please go and say the next thing. It doesn't mean I agree, by the way. It just says I have received the transmission. So you can think about this in that form. I always think about flow control in terms of my advisor's cheery disposition. You can also document fluxes with marble diagrams. Once again, we have the timeline of a flux where time flows from left to right. These are the items that are going to be emitted by the flux, and the dotted lines here indicate there's a transformation that's being applied, like flat map or filter or whatnot. And we usually have a name in there that indicates what's going on. And then the things at the bottom are the results of the transformation, things going through and getting transformed or filtered or whatnot. If all goes well, you have this vertical line here. If something goes wrong, then there's this X. And we'll talk later about how you deal with exceptions that can arise when you're processing a flux, and a mono for that matter, and how to account for them and accommodate them and either continue or resume or fail or whatnot. There are also a wide range of operators for fluxes, and we'll talk about a lot of those. Now, there's also something else called a parallel flux. I'm not going to spend any time really talking about that right now. However, for a lot of what we're going to do in this class, parallel fluxes are actually the way to go because they simplify the programming of parallel computations and give you semantics very similar to Java parallel streams, but there's just a little smattering of asynchrony thrown in for good measure, so they're a little bit more asynchronous than a Java stream is out of the box, because a Java parallel stream is synchronous unless you mix streams with completable futures.